I've got a problem here up on the board. It's actually question number 30 from your textbook. And it gives us this integral, and we look at it, and it's set up already as an iterated integral, so we think, oh, that's often the hard part, we don't have anything to do. And then we say, oh, I don't really like those limits of integration. Okay. Now, a here, I'm saying, is just representing a positive constant. Okay. So I'm going to try to see what this region looks like. I'm suspicious anytime I see square roots and squares, I'm suspicious that I might have circles. And so I'm going to see what this region looks like and see if maybe it's easier to do this in polar. Okay. So I'm going to just draw my region here. Okay. So let's see, y is varying from 0 to a. So if a is up here at this height, this is my bottom boundary and my top boundary. Okay. X is varying from this to this. This is my left boundary, this is my right boundary. Well, if I take a look at that, I'm going to look at just the top boundary first of all. X is the right boundary. X is the square root of a squared minus y squared. Now if I square both sides, that becomes x squared equals a squared minus y squared, but with the restriction that x is non-negative. I want to be careful. Anytime I square both sides of an equation, I run the risk of losing some information about the signs of things. X started out non-negative because it was equal to the principal square root of this thing, so x is still non-negative. Okay. But now if I add over that y squared, x squared plus y squared equals a squared, and x is bigger than or equal to 0. I'm kind of liking that, okay? Because I recognize that this is just the equation of a circle of radius a. This restriction just means that we're talking about the right half of a circle of radius a. So that would look something like this. That's x equals the square root of a squared minus y squared. Now here I can see x is just the opposite of that. That's going to give me the same equation except with x being less than or equal to 0. So that's going to give me the left half of that circle. That's x is negative root a squared minus y squared. So the region I'm talking about then, y has to be between 0 and a, x has to be between the left half and the right half of this circle. We're talking about the top half of this disk. And I'm thinking the top half of a disk is much easier to do in polar coordinates. So I'm going to set up my integral in polar coordinates rather than rectangular coordinates. Okay. So this is my region D. I now need to just describe that in polar. So if it's half of a disk, theta is just going to be going from 0 to pi to give me the top half of the disk. I do need to pay attention to which half it is. Okay. If it was the right half, we'd go from negative pi over 2 to pi over 2. Okay. And then the radius just goes from 0 to a. Remember, we can visualize that by saying for each theta between 0 and pi, that's a constant theta ray. Where am I in D? Well, starting when r is 0 until I hit a, which is when we leave the region D. Okay. All right, so then I need to write my integrand in terms of r and theta. So x is just r cosine theta, and y is just r sine theta. And then dx dy, that was dA. And remember, in polar coordinates, dA is r dr d theta. So now I'm going to want to multiply this out before I do the integration. So we've got the integral from 0 to pi, integral from 0 to a, 2r squared cosine theta plus r squared sine theta dr d theta. I hope that fits on the screen. If it got cut off, I'm about to recopy it, so we're going to be okay. All right. So we now want to do the integral from 0 to pi, the integral from 0 to a. Oh dear. better, of 2r squared cosine theta plus r squared sine theta dr d theta. Oh dear, I didn't dry this board enough. The joys of home videos. Okay, excellent. So let's see, that's going to be the integral from 0 to pi d theta. That's sort of our shell. Okay, and now we're integrating with respect to r. So I'm going to get 2r cubed over 3 cosine theta plus r cubed over 3 sine theta. And that's evaluated between 0 and a. So I'm plugging in a for the r's. So that's going to give me the integral from 0 to pi, 2a cubed over 3 cosine theta plus a cubed over 3 sine theta. And then we just have to integrate that with respect to theta. So let's see, that's going to be 2a cubed over 3. An antiderivative of cosine is just going to be sine plus a cubed over 3. An antiderivative of sine is actually negative cosine, so I'll make that a negative cosine of theta. And then all of that's evaluated between pi and 0. Okay. So let's see, we're going to have what we get at pi, which is 2a cubed over 3, times 0, because sine of pi is 0. Okay. Minus cosine of pi is negative 1. So that's going to be negative 1 times a negative a cubed over 3. That's going to become positive a cubed over 3 minus what we get when we plug in 0. When I plug in 0, sine of 0 is still just 0. Minus cosine of 0 is 1, so minus a cubed over 3. A cubed over 3 minus a negative a cubed over 3 is 2a cubed over 3. So that's how we would evaluate that lovely integral.